All right, and we are moving to the next presentation to be delivered by Professor Nader Engheta from University of Pennsylvania. Nader keeps surprising me by his enormous creativity. Arguably, he's one of the most creative players in this game. And just to mention a few things he did, hyperbolic metamaterials, independently of my colleague, getting Nariman of Epsilon-near-zero materials, which brought lots of interesting applications, ultra-small cavities, and of course moving the concepts and notions from the microwave radio frequency range to the optical range. That also should be credited to Nader. Please join me in welcoming Professor Nader Engheta.
Thank you. Thank you. Thank you very much, Vlad, for a kind introduction. It's a pleasure to be here. I'd like to thank the organizers, Saeed Zohdi and Vinan, for the kind invitation to me to be here today. It's a pleasure and honor for me to give this presentation today. As mentioned by Federico, this year, 2015, is a very special year for all of us in the field of optics and electromagnetics. Actually, there are two celebrations going on in this year. One is that the United Nations General Assembly designated the year 2015 as International Year of Light and the light-based technologies. But also there is another celebration going on, and that is this year is 150th anniversary of the Maxwell equations. And those are the equations that we are very close to our hearts, and we love them, and we work with them every day. So just out of curiosity, I decided to Google to see, what are the other set of equations that consider to be very exciting to the development of the human endeavor and technology. And as I was Googling, I came across this book by Jon Stewart, who is a mathematician and science writer, and his book is entitled In Pursuit of the Unknown, 17 Equations That Changed the World. And actually, you're going to see that in chronological order, I'm going to show you quickly what these equations are. Of course, Maxwell's equation is one of them. But in the chronological order, it's interesting to see the first one is Pythagoras' theorem, and goes back to 530 BC. And logarithms by John Nepper, and we use that all the time. Calculus, the definition of derivative by Isaac Newton. Law of gravity by Isaac Newton. Wave equation by D'Alembert. Square root of -1. I mean, we use that all the time, but that's also extremely important, by Euler. Euler's formula for polyhedra. It's quite interesting, by the way, very simple and yet very powerful. Equality here that relates the number of faces and edges and vertices of a polyhedra. Normal distribution by Gauss. Fourier transform, obviously. Navier-Stokes equations. Actually, Navier-Stokes equation was introduced before our beloved equation, Maxwell's equation, in 1865. Second law of thermodynamics by Boltzmann. Relativity by Einstein. Schrödinger equation, now we're coming to the 20th century. Information theory by Claude Shannon. Chaos theory by Robert May. And the 17th one, the Black-Scholes equation for financial derivatives. Market, we are close to Wall Street. So this would be in 1990. Now, of course, Maxwell's equation is the one that's the closest to our heart, but other equations also, some of the other equations, we use that in our work. And so, again, because of 150th anniversary of Maxwell's equation, I'd like to share with you a personal observation. I was fortunate to have a chance to be in a conference called Faraday Discussions in the Royal Society in London in February. And after the banquet, which was held in the Royal Society, we were walking around in the building of Royal Society, and there were actually fantastic, historical items in the glass windows in that room. And one of the students came to me and said, actually here in one of these windows is the original manuscript by Maxwell. So I took my iPhone and I took this picture. This is a handwritten manuscript by Maxwell, the actual one that was submitted in October of 1864 to the Philosophical Transaction of the Royal Society. And in fact, if you look at this, it actually has 298 million kilometers per second speed that he was calculating there. And, but he submitted this paper to the Philosophical Transaction of the Royal Society. But guess who was the secretary of that transaction at that time? It was George Stokes, Stokes parameter. And in fact, there was a little interesting history written just next to that manuscript that I would like to read to you. It's quite interesting. And so the manuscript was submitted, you know, on 27th of October of 1864, read on December 8, 1864, and printed in June 16, 1865. And particularly, they highlight a very interesting sentence that Maxwell wrote in that paper. He wrote, "The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws." And with that sentence, he changed the world. And after 150 years, we are still, you know, finding very exciting outcome that's coming out of this equation. Before I leave the history and get to actually the main topic of discussion today, I'd like to share one other side issue. When Stokes received this manuscript, he read it, of course, but just like what we do today, you know, the editor will send it also to reviewer. Guess who else Stokes sent this manuscript to review? Lord Kelvin. So Lord Kelvin received the manuscript, and he has this note for Stokes. March 15, 1865. "My dear Stokes, I'm sorry to have kept Maxwell's paper so long. I read it nearly through with great interest almost immediately after it came to me, and I think it most decidedly suitable for publication in the Transactions. If you can allow me to keep it a few days longer, I would be glad to have it till Monday, and unless I hear from you, I shall pass it on that day." So I think Lord Kelvin was also very busy, just like all of us, that, you know, sometimes we are delayed in sending, you know, the review. So some things never change. You know? So in any case, you know, Maxwell's equation had played a very important role in the technological development that we have seen in the past 150 years. And indeed, you can categorize it in two directions. One, in controlling the paths of charge carrier. The whole field of electronics and nanoelectronics and so on is based on controlling the motion of charged particles. But also another way is, of course, manipulating the EM waves. And manipulating the EM waves is done differently. In fact, if you look at this crazy map of a circuit diagram, essentially you can say that this is a metastructure for electronics. Because by having these wires, you decide what direction the current goes and what kind of functionality you can have. Now, for the photons, we need to do differently, of course, and you need to use materials to manipulate photons. And materials could be natural materials, or it could be artificially engineered materials, which is basically the basis behind our conference and our interest in the field of metamaterials. Now, as part of the aspects of metamaterial, one of the areas of metamaterial active is the plasmonic areas. There are many, many interests in this conference in that topic. So if you look at the plasmonic structure, by the way, we know that there are two fundamental features of this. One is the surface plasmon polariton. That would be a surface wave that goes between two media, one of which to have negative permittivity. And another one, of course, as you all know, is the local surface, local plasmon resonance. And all of those, of course, depends on one of this material to be negative. And typically what we do is that we use, you know, things like metal that has a Drude dispersion. And in this Drude dispersion, several parameters play an important role, particularly, the plasma frequency, which is proportional to the number density of charge carriers, and of course, the loss over here. But as we all know, by the way, the loss is bottlenecked there. And often we would like to reduce the loss. That's one aspect. Then another aspect, of course, is the tunability. And the tunability comes through this, changing the number density of electrons, which is not necessarily always easy, but it's doable, and several groups have shown that. But in order to reduce the loss, several, themes and activities have been going on in the past several years. One is to search for other materials. And you heard from Vlad Shalayev's talk yesterday, there's a lot of exciting possibility and alternative to metals. Things like, transparent conducting oxide in this exciting paper by Sasha Botaseva and Harry Atwater, and the refractory materials that you heard from Vlad's talk yesterday, and various different aspects of, titanium nitride and many different aspects of transition metals that we have there. So that's one category of combating the loss, if you will. But another category, as you are familiar with that, is just going back to the dielectric material, but use Mie resonances in order to imitate some of the effect of this resonance. And among those, you just heard from Federico Capasso's, the work on dielectric metasurfaces for achromatic lenses, and the work that the joint effort of Mark Brungesmuth's group and Erez Hasman groups for the dielectric metasurface, and also Yuri Kivshar's group showing that some of the exciting aspects of using Mie resonances in some of the nanophotonic aspects, and the list can go on. Igal Brenner had a very interesting talk yesterday with regard to some of the dielectric structure, and Jason Ballantyne, and so on and so forth. But yet there is a third way that you can actually imitate plasmonics, but with a different capability and that is the concept of structural dispersion that I would like to talk today, as to how that concept can actually imitate effectively a negative epsilon, even though you don't use material with negative epsilon. Now, what do we mean by structural dispersion? Now, if you look at the simplest possible solution to Maxwell's equation in free space, vacuum, is a plane wave. Of course, that's the simplest possible dispersion you can imagine. But when they taught us the wave equation, the next solution to Maxwell's equation usually deals with waveguide structures. So waveguide structure, of course, has been around for many decades, in microwave, in optics, and so on. And if you consider basically simplest possible structure, two parallel plates made of perfect conducting metal, empty inside, just a simple air or dielectric. The first things they teach us in waveguide, the theory, is TE10 mode, simplest possible mode. And I'm not considering TEM mode, it's a TE10 mode, is the one that the electric field is parallel with this. And of course, we all know that the distribution of electric field and magnetic field within these plates would follow this one structure, which in fact there's a longitudinal component, obviously, for the magnetic field over here. And then these two expressions, you see that it varies sinusoidally. But the wave number that, of course, would follow the expression that comes directly from solution to Maxwell's equation and satisfaction of the boundary condition. Now, this, of course, has been around for more than 100 years. But one of the interesting aspects is that if you look at the wave number over here, that you can write it in this form, this expression effectively behaves as effective epsilon. Now, if you actually go and sit in the middle plane over here at the point z equal to a over 2, you only see these two components of your field, which is both transverse component, and at that particular plane, the longitudinal component of magnetic field is 0. So to the observer in that middle plane, it looks like a transverse plane wave, moving with a wave number of beta. Effectively, that wave would see an effective permittivity, which looks like this. Now, if you look at this effective permittivity, this one directly shows the bulk permittivity that you have over here, whereas this expression over here comes from satisfaction of the boundary condition. However, if you take a look at this, you see that is exactly the Drude model that you have over here. And yet, the waveguide is empty. In other words, the equivalent of omega p squared that we have in the free electron type of material that we are familiar with in metal, here is replaced by this term, which is directly related to the separation of the waveguide. In other words, here, by just moving the plates of the waveguide, effectively you can change the equivalent of plasma frequency that we want to change in metal. But here you can do it by just basically movement of the metal there. Now, this concept of parallel plate waveguide imitating plasma has a long history. In fact, the earliest paper I was able to find is belonging to 1962 by Walter Rotman, who actually was working in antenna designs, and he wanted to actually imitate plasma by parallel plate waveguides. Now, in that paper, by the way, you see a reference to another earlier paper by Brown, who actually imitated the plasma with metallic wires, so to speak, the wire medium. But this was, to the best of my abilities, the earliest reference I was able to find that would show this parallel plate waveguide imitating plasma. And in fact, this is the picture from his paper, and he had to actually put a resistive sheet over here to actually bring a little bit loss into that Drude model, so to say. Of course, he didn't call it Drude model, we call it Drude model. But it's completely opposite to what we want to do here. We wanted to reduce the loss. He wanted to actually increase the loss in order to make it similar to plasma. Now, this technique, by the way, over the years has been used by various different, activities in order to imitate what we like in plasma. For example, in 2008, we used this concept to experimentally verify the concept of E and Z supercoupling that we had introduced with Mario Silverinha 2 years earlier. And indeed, by having a metallic waveguides over here that operates at cutoff, you can imitate epsilon-near-zero. And indeed, we show that. Now, 5 years later, joined forces with my good friend Albert Polman in Amolf in Amsterdam to see whether experimentally would be possible to show the same effect of waveguide at cutoff in the visible domain. And indeed, in Amolf, this structure was designed, in Albert's lab, that you see that this structure is very similar to the waveguide structure I mentioned to you, but for the visible structure. And sure enough, with his cathodoluminescence, spectroscopy, here we showed that indeed it's possible that at cutoff frequency, this structure behaves as epsilon-near-zero. Now, Vlad Shalayev and Igor Smolyanov also used this concept of waveguide, but in the tapered version of that, to actually show the optical cloaking using the transformation optics, to have the optical cloaking and invisibility there. But even though these parallel plate structures imitate plasma, they have a fundamental limitations. And just recently, we were able to come out with a solution to overcome this fundamental limitation. Well, what is this fundamental limitation? Okay, let's go back to this structure. So we have two metallic plates, and the region in between of that, let me assume, is filled with two different actual material with epsilon over here. And if you follow this formula that I showed you, which is effectively equivalent to the Drude model, by controlling different value of epsilon over here, both of which are positive, simple dielectric, even air, and controlling this A, you can actually create any effective epsilon you want over here. So we decided to see what would happen over here in the structure. So imagine you have the things here. The actual epsilon is 3. The actual epsilon is 5. By controlling A, you can have an effective epsilon 1 and effective epsilon 3. And if you launch a TE10 mode from here, and you go in the middle plane and look at the field distribution in that middle plane, you see this. Okay? It's very similar to what you would expect if you actually have a material with epsilon 3 and material with epsilon 1 over here. However, this has a problem. The problem is if you look at the power in the TE10 mode that's coming in this direction, and the power in TE10 mode that's going there, if you add those two power, it's less than the incident power of the TE10 mode that's going there. So where did the rest of the power go? The system is completely lossless. Hold on to that. There is another, feature that shows there is a fundamental limit over here. We all know, by the way, that one of the milestone of plasmonic resonance is local plasmon resonance. So if I have an infinite cylinder with epsilon -1 and outside epsilon +1, and you illuminate a wave with the electric field normal to the axis, this will go into resonance. That's the local plasmon resonance. So we said to ourselves, let's try to see whether we can imitate this under that waveguide. So we went back to this geometry. This is, in our simulation, we assume this is PEC walls. Here we put the material with actual epsilon 3. Here we've had the air over here with actual epsilon 1. By deciding what this A should be, then the effective epsilon here becomes 1, and effective epsilon here becomes -1. So then we launch a TE10 mode over here, and we look at the field distribution in this plane, and if indeed this structure imitates plasmonic resonance, we should see a resonance. We didn't. The resonance did not come out. Why? This added to that puzzle again, over here. So no plasmonic resonance is observed in this simulation. So we spent some time on this to find out what caused this and how we can actually solve this. And then we found out what the problem is. The problem is, of course, is a cross-mode coupling. So when you send your TE10 mode over here, which has a transverse component E sub x, longitudinal component H sub y, and the transverse component H sub z, when this one is propagating and hit an oblique interface, it has to be oblique interface, this longitudinal component is going to actually create a little bit of TM10 mode there. And TM10 mode has the same cutoff frequency as TE10 mode in the parallel plate waveguide. So part of the energy of the TE10 mode couples into TM10 mode, and we don't want that. We want to keep the mode purely at TE10 mode in order to completely imitate the plasmonic effect with all positive dielectric material. So the question to us was that, how can we get rid of this coupling? So we have to introduce something else in this waveguide in order to kill this mode coupling. And we came up with the solution. And the solution is to put tiny wires along that interface. The tiny wires would actually short circuit the E sub z component that is one of the cornerstones of the TM10 mode. TE10 mode does not have electric field in the z direction, but TM10 mode does. And if we put the tiny wires over here, those tiny wires would not affect the TE10 that's coming, but it's going to short circuit the TM10. So we said, let's see what happens if our simulation we introduce that. So we launch the wave, we put this tiny wire in our simulation, and we look at the field distribution in the middle, and sure enough, we have resonance now. It's quite interesting that this resonance happens even though the actual dielectrics that you put over here are positive. Positive. One of them is air, the other one is dielectric 3. Now you might say, okay, well, the reason you see this resonance because these wires are about Landover 2. Actually, they're not. They're shorter than Landover 2, but in order to show that this is not just because of the length of the wire and the materials plays a very important role, we did the following. We went back to this simulation and we made two materials the same. Epsilon actual 3, so effective epsilon 1, effective epsilon 1. But the wires are still there. And then we ran the simulation and nothing happened there. So material plays a very important role. So with the positive dielectric, you can create plasmonic resonance with this technique. So we did a parametric study over here with that structure, and we gradually change, the epsilon actual over here, and sure enough, around 3.16, which effective epsilon is -1, you hit the resonance over here, and significantly enhance field near these wires. Now, we said, okay, in order to do that, we should show that whether we can have surface plasmon polariton. So then we designed this structure. Under the waveguide, actual material 4, effective material 1, actual material 1, effective epsilon -2. And in our simulation, we put these wires over here. We put a little dipole over here. We excited dipole. And we look at the field distribution in the middle plane. And that's what you get. This is very similar to the surface plasma polariton that you have over here, and yet, please note that the dielectric here is 1 and dielectric here is 4. So you can create effectively a surface plasma polariton at the interface of 2 positive dielectric media by putting the tiny wires on top of that. And then we compare that with the formula that we have from surface plasma polariton, and quantitatively also it agrees. Actually, in other words, if you put in this formula the effective epsilon that you have under this waveguide, it will actually show you the wave number for that SPP you have. This is not spoof plasma. I'd like to emphasize that. This is not spoof plasma at all, because spoof plasma works based on the mode inside the holes there. There is no hole over here. This is just putting a tiny wire to kill the coupling to TM10 mode. And you can bend it, and it works nicely, no problem. Now, I want to show for the rest of few minutes that I have 2 interesting concepts that can benefit from this. Now, several years ago, Harry Atwater and Stefan Meyer did a pioneering work by showing that if you have a plasmonic particles next to each other as an array, you have a beautiful type of waveguiding going from particle to particle. So if you have this plasmonic particle with epsilon negative, like a silver and gold, and you illuminate that, then you have this very nice waveguiding effect that they showed quite successfully at the beginning of the field of plasmonics. So we said to ourselves, is it possible to actually design something like this, but entirely with positive material? In fact, better yet, entirely with air. Could we do this? So we decided to design something like this. In this case, this is a metallic waveguide, and you actually create these holes inside of this. So let me cut and show you the inner structure over here. So remember, everywhere that you see over here is air. This is just air. It's just the boundary is a perfect conductor that you have there. You have these tiny wires over here. But this height is different than this height. So if we use this formula, epsilon b is 1. Oops. Epsilon b is 1, but only is 2 different a. One a here is different than this a. So we do it such that this epsilon become effective negative here and effective positive over here. And let's launch a TE10 mode through this. This is the structure that you see from here, and it works. So essentially, that guiding that Stefan and Harry showed for the plasmonic nanoparticle can be actually imitated in other frequency regime as long as we have impenetrable walls for the structure with the tiny wires there. And the last item I want to talk about is that how we can use actually this phenomena in order to show some of the other areas that we are working on, namely with the extreme metamaterial, Epsilon-near-zero, which we had already shown experimentally, this technique could prove that for us. And now our interest is on EM and Z, epsilon and mu near zero structures. And one of the interesting features of this epsilon and mu near zero structure is how they actually behave in cavities. Now, we all know, by the way, that if we have a regular, cavities, is that if you have a closed cavity, let's say ideally is a perfect conducting wall with air inside, this cavity, of course, has a very, very high Q and has certain, resonant frequencies. But we all know that if we get this cavity and we deform its body like this, obviously the resonant frequency will change. So one of the things we are interested is that is it possible to have a deformable cavity whose resonant frequency does not change? Because we are very interested in the concept of flat photonics and deformable photonics. And if we can do that for cavity, that could be quite interesting. So one of the areas that we are pursuing is that what if we can have a cavity that we can fill it with EM and Z material? Because inside the EM and Z material, the wavelength apparently would be infinitely long, so the shape should not matter. That was our intuition there. The question is, how do we make EM and Z material? Now, back in 2007, in a paper that Mario Silverinha and I published, we showed that if you have a periodic structure in which the host is epsilon-near-zero, but we put a dielectric rod inside of this, you can design this dielectric rod such that the effective mu of this structure would also be 0, in addition to epsilon being already 0. And it turns out, by the way, that if this dielectric rod happened to have a circular cross-section, the formula actually would be this, which is, relatively speaking, simple formula. I would like to highlight a point over here, that this simple formula that you can find in this paper, it actually depends on the area of this cell, not on the shape of the cell. So in other words, you can get this area, you can actually deform it in any shape you want, as long as you keep this area fixed, the effective mu that you have from that should work. Now that's one way to make effective epsilon and mu near 0. But there's another way to have the effective index near 0, and that's done by Professor C.T. Chen, that he has shown that you can have, with the photonic bandgap structure design, a Dirac cone dispersion and accidental degeneracy. At that point, you can actually have effective index to be near 0. And my good friend Eric Mazur's group has done actually experiment on those photonic bandgap structure with the Dirac cone, that they show that indeed, you can have effective n near 0. Now, so if we get our structure, not the photonic bandgap one, in this one, that you have a dielectric rod within an ENZ structure, we decided to study this, the resonant concept of these cavities. So what you see over here, by the way, is a series of simulation that my graduate student Ahmed Mahmoud, who is here in the audience, has done beautifully over here. In this simulation, what Ahmed has done is that he considered a metallic PEC wall with a host of background being epsilon-near-zero, and then have a dielectric rod over here and trying to find the eigen mode of this cavity. And what you see over here is the field distribution, electric field, and the color is the magnetic field distribution that you see over here of that cavity for that given frequency. Now, what would happen over here is that what happens if we move the dielectric rod? In a regular cavity, if you do that, the resonant frequency will change, but not here. You can move it here, same resonant frequency. Different field distribution, but same resonant frequency. Move it here, same resonant frequency. You can keep the area, but just change the shape. All of these will have the same resonant frequency. You can deform the cavity, as long as you keep that area the same, you get the same resonant frequency. This is quite exciting, because this is a kind of cavity that can have a high Q from the temporal point of view, but actually quite flexible from spatial point of view. Now this is for the two-dimensional case, and I remember when I was, on some occasion I was talking about this, and Agustin Arbas, I know somebody in the audience right there, you asked me this question, can this be applied for the three-dimensional cases? Yes, we have done it now. In fact, you can do it in the three-dimensional cases in this form, but Agustin, this is actually even better than 2D, because the constraint of volume is not here anymore. You can actually even squeeze it and change the volume, and it still works, as long as this dielectric sphere that you have over here doesn't change. So in this set of simulation that my postdoc Inigo Liberal has done, you can see the magnetic field distribution of this silicon sphere within the epsilon-near-zero structure, and the distribution of the electric field over here. And if you actually change the geometry of these, as long as that sphere inside is not changed, the resonant frequencies stay the same, regardless even of the topology. Here, for example, we have a topology that there's a hole, just like a torus. Here, you introduce some foreign objects in this area. Here, you actually change the boundary. All of these would have the same resonant frequency. So you can gradually deform this, you can continuously deform this, and it still works. However, what you change over here is the Q. So this is actually a very interesting, unusual, peculiar cavity. Its resonant frequencies stay the same when you deform its shape, but its Q will change. So that could be quite interesting, because you can decouple these two phenomena. Often, when we design a cavity, resonant frequency and Q are tied together. So, but here, you don't have to do that. You can design your cavity for the frequency you want. You can deform it. You can have a deformable cavity, and that will actually change your Q, but not your resonant frequency. In this set of simulation, as we've shown over here, The Q can change, but the resonant frequency stays the same for that. And this point that you see over here is the effect that you basically dent into this cavity. So as you increase the amount of dent, resonant frequencies stay the same, but the Q will change. And Q should change because the field distribution inside will change. And by the way, in this structure, we put a realistic parameter for this. In fact, for epsilon-near-zero in this simulation, we use silicon carbide with the imaginary part of that 0.1, and still the system works. So system is actually quite robust, even to loss over here. And you can see even for this, the Q that we got is about 500 over here. Now, finally, to close, is that now what we are doing, we are in the middle of the experiments to actually show these cavity properties. Two members of my group, Ahmed Mahmoud, my graduate student, and Brian Edwards, my research scientist, actually are in the middle of this experiment. So what has been done over here, Ahmed and Brian designed 3 different cavity structures, same cross-sectional area, but arbitrary shape over here. And the height is decided to be around land/2 in order to keep the background effective epsilon-near-zero. And the dielectric rod, we assume 3 arbitrary location. We can put it in 3 arbitrary location. And the input and output port also 2 arbitrary location on this. This design has been done. The structure has been built and it's in our lab. In fact, this is a picture of one of them over here. And now you notice those tiny wires that I was mentioning to you. So in the design, Ahmed and Brian also designed these tiny wires in order to prevent the mode coupling to TM10. That's very important over here. And so we are collecting the data right now. The experiment is not finished yet. So far, the data that Ahmed is collecting shows the promising directions, that indeed this will turn out to be the same resonant frequency for all of these. In fact, in this structure, this is the simulation done by Ahmed, that we showed that for that specific geometry that we have built, what should be the expected resonance of the system. And you notice that this resonance stayed the same for all 3 of them, but not the other resonances, not the higher resonances. The other resonances, the background would not be ENZ anymore, but for this one, it's the same. This is a simulation. We are hoping by the time we finish the experiment and then compare it with this, it will show the agreement. That remains to be seen. So we are very interested in this cavity, particularly from the point of view of quantum electrodynamics. As Vlad mentioned yesterday in his talk, and I agree with him completely, I think one of the very exciting direction of the field of metamaterial and plasmonic is in the quantum optics. Some of the peculiarity of this cavity could play a very important role in quantum optics. We are interested and we are in the middle of studying superradiance, subradiance, long-range collective state of multi-emitters of this structure, long-range entanglement, and last but not least, the cavity quantum electrodynamics. What kind of cavity quantum electrodynamical variation we should have when we deal with this kind of peculiar cavities? What kind of long-range entanglement we will have? These are some of the things that, in my view, field of metamaterial can help us. So with that, let me come to the summary that Maxwell's equations have been around for 150 years. And still, by the way, give us a lot of interesting inspiration. And particularly in order to control photon and electromagnetic waves, we need materials. And materials are the one that can manipulate the photons. And the whole field of plasmonic and metamaterial that we all like and we gather here for that purpose could provide us with a very interesting metaplatforms, if you will, in order to manipulate wave and material interaction, both from classical aspects as well as the quantum optical aspects for that. With that, I thank you very much for your attention.
All right, thanks a lot. Well, the paper is open for questions. Nikolai. I'm sorry, what infinitely large volume?
Oh, you mean you're talking about this particular cavity?
Nader, could you please repeat the question?
The question is the following. Correct me if I'm wrong, if I misunderstood your question. In the case of cavity that I mentioned, with the effective epsilon and mu near zero, Nikolai is asking what would happen if we gradually increase this structure? What happened to the resonant frequency of that? The resonant frequency, by the way, of this cavity is locked with the plasma frequency of E and Z. Now, if we increase this structure over here, the plasma frequency, of course, doesn't change, but the Q will change. Because when you have the imaginary part of epsilon of E and Z, of course, the field distribution changing, and the Q will change. So Q you can control. Now, if the Q is going to go down. Yes, absolutely. That's right.
David?
David. Effectively minus 1. Yeah. The waveguide structure. Yeah. That's right. No. Okay, let me clarify. The question is that when we have the material epsilon such that the effective epsilon, the ratio would be -1, that would give us a singularity of Maxwell's equation, which I agree with you in that regard. And what happens, the second part of your question with regard to that energy of the TE10 mode. Let me start, by the way, with the second part first. Now, when I said that when we launched in this simulated structure with the TE10 mode, and we look at the TE10 mode and TE10 mode here, when you add those two, it would not become the one. That, if you just look at the energy or power in the TE10 mode, that looks like somewhere the energy is lost. But the energy has gone into TM10 mode. So there is no problem with the conservation of energy. In fact, that structure was not in the case of -1 and +1. If you remember, in that case, the effective epsilon was 1 and 3. So that was not the case at all. So the energy is conserved, everything is fine. It's just to prevent it from going from one mode to the other. Now, coming back to the first part of your question. Now, remember that all of the cases that I showed over here, intentionally I used the positive epsilon, but by controlling the A, effectively epsilon become -1. And intentionally I chose the one that would give us a resonance. Now, that was actually a very interesting point that you raised, because in actual material, epsilon -1, actual material with epsilon -1, the direction of the electric field is opposite to each other, because the normal component of D has to be continuous. That's one of the reasons actually these wires are necessary there. Because if we don't have the wires there, effective epsilon could be -1 or +1, but the actual epsilon is both positive. So the normal component of D has to be continuous. In order to do that, you have to have the wires. And that singularity that you're referring to, it happens if the diameter of the wire goes to 0. If the diameter of the wire goes to 0. Now, the diameter of wire is not 0 in this case, precisely to prevent that singularity. Yes. Yeah. Okay, good point. Now, the ENC value over here that we are using, we use it, let's say, through the model, and you're operating near omega p. That's right. In the case of three-dimensional, by the way, that we actually use the parameters from the literature for the silicon carbide, because we want it to be as close to the realistic possibility as material as possible. So if you look at, for example, silicon carbide at the frequency of 10.3, at the wavelength of 10.3 micron, real part of epsilon would be near 0. Imaginary part of it would be around 0.1. It could be even better. my friends from NRL telling me that actually could be even better than 0.1, but we want it to be on the conservative side. That happened. Now, if we change the frequency going above and below, obviously the system would not be resonant anymore. Remember, the Q is high, but it's not very high. It's about 500. So when you change that, the cavity would not get excited unless you bring the Q down. I can talk to you more on the detail of that. Yes. Yeah. Very good question. First of all, by the way, those was just symbolic because we wanted to show if we change the volume over here, what would happen. But remember, in that case, we also had the dielectric sphere in our simulation in the middle. So let me rephrase your question a little bit more generally. What you're saying is what would happen if we have an indent into the cavity wall such that it actually touches the dielectric in the middle and the E and Z would disappear. If that happens, by the way, then of course the two cavities would be separate. And then effective Epsilon-near-zero would not happen. You have to make sure that the Epsilon-near-zero structure would be continually there. You cannot make it two separate segments of that. It should be basically simply connected region, so to speak, from mathematical language. It should be a simply connected region. So what we showed there in our simulation, and that was a simulation, by the way, we haven't built that yet. That would be some of the things we would like to do later. That if you actually punch this cavity wall over here, the field distribution will change, and that field distribution change would change the Q of the cavity. But you have to make sure the E and Z stays there.
All right, let's thank again Professor Engheta for this.
Thank you.